Hello friends, welcome back in this video session of pharmaceutical analysis. So today we are discussing the last part of these complexometric titrations. In the previous three parts we have already covered all the fundamentals, principle and the types of complexometric titrations. So the link for those three videos is given in the description box. Now in the today's session our main focus is on the masking and demasking agent used in the complexometric titrations. Now this concept is very important and it is very interesting in the complexometric titration. So first we should understand why we need to use the masking and demasking agents. Okay, so in some of the titrations only masking agents are used, and in some of the titrations we use masking as well as demasking agent. Now here I have given one table which is indicating the name of the indicator and what color change it is giving and at what pH it will be effective. And with this particular indicator, this can form complex with these metal ions like calcium, barium, magnesium and so on. So what here we want to say, with one indicator you can detect multiple kind of ions which are present as your sample. Okay, now as I mentioned in the earlier videos, the EDTA, which is used as a sequestering agent or the complexing agent, this is very widely used in all the complexometric titration. And the problem of EDTA is it is very unselective. That means you can say as a problem, or you can say as a advantage. So we have seen the properties of the EDTA, why it is widely used as a complexing or sequestering agent in these complexometric titration. So one of the advantage we can say it is unselective, so it can form complex with many metal ions. But what if you have the sample which contain the multiple ions? Okay, now consider for an example, you want to estimate the purity of the calcium ions in the given sample, but this calcium ion has some impurities of barium ions. Now in such case what happens, when you take your calcium ions which has some impurities of barium ions and you prepare a solution of this, you will add buffer, solvent and so on, and then you will add an indicator, right? Then when you start the titration with the EDTA, EDTA can form complex with both the ions because it has a capability, it is a hexadentate ligand and it can very easily form a complex which is more stable complex with that of the calcium as well as with that of the barium. So obviously what will happen, the amount of EDTA which is consumed in the course of titration will be more than the actual required by the calcium ions. So if you calculate with the same burette reading the purity, obviously the purity will be false, it will give the false reading which we cannot rely, and this is happening because of the presence of some metallic impurities present in the sample. Okay, so in such case we have to use certain methods in which we can remove the interference of these metallic impurities. So there are different ways by which we can remove these interferences, and one of the popular method to use is the masking and demasking agent. Sometimes what happens, in a sample we have number of metal ions not as impurity but as the analyte. Okay, so there is a possibility that I have certain pharmaceutical preparation in which I have a barium as well as a calcium, so they are not present as impurity but I have a mixture of these two. Now in this case, can I estimate the purity of these metal ions by complexometry? Okay, so that we need to consider, and this can be answered or this can be solved by the masking and demasking agents. Okay, so we'll see what are the ways to increase the selectivity of the complexometry. So we can increase the selectivity to get accurate results, we can increase the selectivity so that in presence of other metallic ions, because we have mixture of ions in some of the formulations, so though we have mixture of ions, can we estimate, can we quantify all of these metal ions by the complexometry? So it is possible, yes, it is possible, right? So what we can do, the first way to increase the selectivity, we can control the pH. Okay, we know some of the metal complexes are stable at a particular pH, whereas the other, they are not stable at a particular pH. So for example, the bismuth in presence of alkali earth metals. Now let's say you have alkali earth metals as a impurities and your analyte is bismuth. Okay, so what you can do, you can do the complexometric titration in the acidic pH, slightly acidic pH. So what happens at acidic pH, alkali earth metals, they do not form the stable complex, they remain dissociated. So they will not form a stable complex with that of the EDTA, and they will not interfere in the detection of your bismuth ions. Okay, so bismuth can easily form a complex with the EDTA even at the alkaline pH. So what we are doing, we are selecting a pH in which only the analyte is able to form a stable complex, whereas the interferents or the impurities, they are not able to form a complex with the EDTA. So in turn, they will not interfere in the final quantification. So this is one of the way we can improvise the selectivity of the method. Second way, we can use the selective metal indicators. For example, we already see in this particular table, so I have abstracted these two indicators. One is a metallochromic indicator, here the modern black 2 and murexide. So you can see the calcium, barium, magnesium, these are the ions which you can quantify with the modern black 2, whereas the cupric ions, so you can see the cupric ions will not be detected if you are using the modern black 2. So suppose if you have the calcium and cupric ion in a mixture or in a sample, so if you want to estimate only the calcium, you can use the modern black 2 mixture. So this modern black 2 mixture is not forming a complex with that of the cupric ions. So this is how you can use the selective metal indicators to remove the interferences. We can also use the classical separation. So there are various classical separation methods. We can utilize those and we can separate the interfering substances or the metal impurities, and then we can do the titration selectively. Then we can also utilize the solvent extraction method. Okay, so there are various solvent extraction method. By using a separating funnel, we can again isolate the interfering metallochromic impurities or the substances, and we can do the titration. Then we can also remove the anions, especially we can use the orthophosphate kind of anions by using a this ion exchange resins are there, ion exchange chromatography is there. So with help of that, we can also separate out them and we can selectively quantify them. And then finally, masking and demasking agent, which are very popularly used in these complexometric titration, and we could see many times there are frequently asked questions based on this particular masking and demasking concept. Okay, so masking agents, they act either by precipitation or by formation of complexes which are more stable than that of the interfering ion EDTA complex. Okay, so there are two ways by which the masking agents can react or they can act. One is they will precipitate the interfering substances or they will form the complexes. So masking by the precipitation. Okay, masking by the precipitation. So in this case, there are many heavy metals, like cobalt, cupric, lead. These can be separated either in the form of insoluble sulfides using sodium sulfide. So we can use sodium sulfide and we can selectively precipitate these ions. Okay, or we can make them as a insoluble complexes using the thioacetamide. So here the main principle is we have to precipitate the interfering metal ions. It could be as a impurity or it could be as a substances in the given sample. So these are filtered then or can be decomposed and then titrated with the disodium EDTA. Other common precipitating agent are sulfate for lead and barium. Okay, so you can use sulfate for precipitating lead and barium. You can use oxalate for precipitating calcium and lead. Similarly, fluoride for calcium, magnesium and lead, ferrocyanide for zinc and cupric ions, and 8-hydroxyquinoline for many heavy metals. So we have seen 8-hydroxyquinoline. This is again a complexing agent, right? It has a quinoline ring and 8-hydroxy functionality, so it can precipitate the heavy metals. Then similarly, thioglycerol is used to mask the cupric ions by precipitation in the assay of lotions containing cupric and zinc. Okay, so we want to estimate the zinc, and this is impossible if the cupric ions are present. So what I will do, I will add thioglycerol. Thioglycerol will precipitate the cupric ions, and because they are precipitated, now they are not interfering in the estimation of zinc. So this is how we are utilizing this concept by precipitating selectively the metal ions. Then another way is masking the interference or the metal ions by the complex formation. So masking agent, they will form more stable complex with the interfering metal ions. So the most important aspect is that the masking agent must not form complexes with the metal ion under the analysis. Okay, so let's say we have two ions, metal ions, and the one which is interfering, only with that the masking agent should form a complex. It should not form a complex with the analyte which you want to quantify, otherwise again it will be difficult to estimate. Okay, so it should selectively precipitate or form a complex with the interference, not with the target analyte whose quantity you want to find out. The different masking agents are used as enlisted here, like mercury, cadmium, zinc, arsenic and so on. You just can read those. So these are the agents which we can use it as a masking by forming a complex. Ammonium fluoride will mask the aluminium, iron and titanium by the complex formation. Similarly, the potassium cyanide react with silver, copper, mercury, iron, zinc, cadmium, cobalt and nickel ion to form complexes in the alkaline solution, and these are more stable than the corresponding EDTA complexes. Okay, so EDTA cannot displace them, and hence we can utilize them in the quantification. So the other ions which are present in your sample like lead, magnesium, manganese and the earth metals, you can determine even the other impurities like these ions are present in the sample. Okay, so we will see with the suitable example how they are helpful in the quantification. For example, here you can see I have a sample which is a mixture of lead and zinc. Okay, so the one possibility is that it could be a mixture of these two, or the other possibility is that my analyte is lead and zinc is present as a impurity. Now what I want to do, I want to selectively quantify the amount of lead present in the sample. So if I am simply doing a titration by adding solvent and buffer and indicator, EDTA can form complex with both of them. Okay, so in this case I am not able to find out the amount of EDTA consumed by lead. So in fact it is the amount of EDTA consumed. Burette reading is nothing but amount of EDTA consumed by both of them. Okay, so what we can do, we can add here the masking agent, for example the potassium cyanide. Now this potassium cyanide will act as a masking agent and it will mask only the zinc ions. Okay, so what is happening here, masking agent is selectively acting or forming a complex with that of the zinc, whereas it does not react with the lead. So you can see the lead is as it is, whereas the cyanide ion have formed complex with the zinc, and this zinc cyanide ion complex is very much stable. So even if you are adding the EDTA from the burette, EDTA will not able to break this complex because this is more or highly stable. So what EDTA will do, EDTA now will react only with the lead, and the burette reading what you are getting, that is only because of the lead EDTA complex. Okay, so you can easily find out the amount of lead present in the given sample, that is very accurate concentration. Now if you want to find out the amount of zinc also in the mixture of this lead and zinc. So what we can do, we can now demask the zinc. Now here the EDTA was not able to break this complex. This was quite invisible to the EDTA. Now because of the masking it was invisible. Now if we demask it, now EDTA can form a complex with that. So I will use a demasking agent. For example, formaldehyde we will add in the same conical flask. Now what will happen, because of the addition of formaldehyde, zinc cyanide complex will break and zinc will be present in the free form. Okay, now this zinc then can be titrated with the EDTA, and then we can also quantify the content of zinc in the sample. So this is how we can estimate the amount of lead as well as amount of zinc in a given sample as a mixture. So this is the use of masking and demasking agent. We will take one more example which is very interesting. Now we can analyze three different metal ions which are present together in one sample. What these are? The cupric ions, cadmium ions and calcium ions. Okay. So what I have done, I have taken this sample which is a mixture of these three metal ions, and this I have dissolved in a suitable solvent. Then we are adding buffer here, we are adding suitable indicator here, and now we are going to quantify each one of them. So here how we can quantify each one of them without separating them from each other, we can utilize again masking and demasking agent. Okay, so this will be done in three steps. In step 1, what we will do, we will take our mixture or the sample which has these three ions, then we will add the indicator, solvent and buffer, and then we will start the titration with the standard solution of EDTA. Okay, then what is happening, as we have not masked any of these metal ions, EDTA is able to form the complex with all of them. So here the burette reading is relatively higher. So more amount of EDTA will be consumed because all the ions one by one they are getting complexed with that of the EDTA, and finally the indicator will be released in the free form, and then we will get a color change. Now suppose in this particular step 1 I got a burette reading as 30 ml. So we can note down this, and then we will proceed for the next step, step 2. Now you can see in step 2 what we are doing. In step 2 we will add the masking agent, okay, to the mixture. Okay, so in step 1 this titration is done, then we can discard this, we can take a next fresh conical flask. Again we will take the same sample which has the mixture of these three ions, and then we will add the potassium cyanide to it. Okay, of course we will add indicator and buffer and all those things, and then we will add the potassium cyanide. Now this potassium cyanide is acting as a masking agent, and it is selectively masking the cupric and cadmium ions. I can see the cyanide is not able to mask the calcium. So there is no reaction of cyanide and calcium. Because of the no reaction, calcium ions are present in a free form. So if you start the titration with EDTA, EDTA can form complex with the calcium. Okay, whereas because of the cyanide ions, it has formed complex with cupric and cadmium. This is relatively more stable complex, and because of the more stable complex, already this complex is produced, and hence the EDTA cannot break this complex and it cannot react with cupric and cadmium ions. So in second step, the burette reading what you are getting, that is only because of the formation of calcium EDTA complex. That means, in other words, we can say the 15 ml burette reading what we got here, for example. So this is the amount of EDTA consumed by only the calcium ions. Okay, though cupric and cadmium ions were present in the flask, but what we have done, we have masked them, we have hide them by reacting with the cyanide ions. Okay, so let's say in step 2 we got 15 ml reading. Now we will be doing step 3. Now in step 3 what we will be doing, we will be demasking the ions. Okay. Now what we will do, we will add the demasking agent like the formaldehyde. Okay, HCHO, that is nothing but the formaldehyde. Now when we add formaldehyde in this particular same solution, this is the same solution, right? So in the same solution we will add the formaldehyde. Now this formaldehyde will demask the cadmium ions. So it is, formaldehyde is capable to break this cadmium cyanide complex and it will release the free cadmium ions, whereas the formaldehyde is not able to break cupric cyanide complex. Okay, so it remains as it is. So after demasking the cadmium, we can start the titration. Then we will add the EDTA from the burette. Now EDTA will react only with the free cadmium ions and it will form cadmium EDTA complex. In other words, here the amount of EDTA which is consumed, that is consumed by the cadmium ions. Now let us say if here I got the burette reading of 10 ml, that means 10 ml EDTA is consumed by the cadmium. In step 2, 15 ml EDTA is consumed by the calcium, and in step 1 it was 30 ml that was consumed by all these three ions. So we know the total reading, we know the reading of calcium, we know the reading of cadmium. So obviously if we know these three things, we can do the estimation of volume of EDTA consumed by the cupric ion. Sorry, it is a mistake here. So this is a cupric ion, it is not cadmium here, it is a cupric ion, not Cd, it is a Cu. So Cu is equal to 30 minus 25, so that will be 5. So 5 ml is the amount of EDTA consumed by the cupric ion. So this is how we can utilize the masking and demasking agent, and we can selectively quantify the multiple ions present in the given sample. I hope you have understood the concept of masking and demasking agent. Thank you for watching it.